4.4, De Moivre's theorem. So first, let's recap about when we have an imaginary number, a complex number, and if we want to write it in trig format. So here's my r, that's like our radius, that's our magnitude. And then we have our real component, like our x, that moves left and right, and our imaginary component that moves like our y, up and down. Now, if we were to square this, so z times z, we talked about when we multiply two complex numbers together, trig numbers together. So if we have z times z, this becomes r times r, which is r squared, and then we would add theta plus theta, which would give us 2 theta. If we had z cubed, so if we took this and we multiplied it by z then we would take this r squared times r, that would be r cubed, and we have 2 theta plus theta, that would give us 3 theta. See how this pattern is recurring? So if we have z to the fourth, we would have z or r squared times r squared, and then we'd be adding. So that is De Moivre's theorem. If we have a complex number written in trig format, where n is a positive integer, so n right here is raised to what power, then that same format is saying, when we were bringing this into whatever power, the radius raised to that power, and then the angle times whatever power you're raising it to, because that's how many times you're going to be adding that number to itself. So if I'm looking at this, the first step I'm going to be doing is I have to figure out my r is. So if I'm finding my r, remember that is our magnitude. We're taking the square root, that would be -1 squared plus, here it's just the square root of 3 squared. So this becomes 1 plus 3, which is the square root of 4, which is 2. Now I also need to figure out my angle is. So my angle here is going to be tangent of my theta is equal to my b over my a. My b over my a. Now if I were to plot this on my grid, my real and imaginary, this is moving to the left 1 and up square root 3. So now I know that this angle is in the second quadrant. Now if I use my tangent, and if I make this right triangle, this is my opposite over my adjacent. So opposite of square root 3, this would be a reference angle of 60. But when I'm writing this, I want you to be writing it with radians. So unless if it gives you degrees, you should be using radians for this formula. So if this right here is 60, that's the same thing as pi over 3. So this is 1 pi over 3. Right here, this angle would be 2 pi over 3. So now my theta is equal to 2 pi over 3. So I'm writing this now. I'm going to have my z to the 12th is equal to 2, my r raised to the 12th power, and then in parentheses, cosine of, now n is equal to 12 here, so 12 times 2 pi over 3, plus I sine of 12, 2 pi over 3. And then I have to simplify. So 2 raised to the 12th power is going to give me 4,096. Now sometimes people are confused of how to type this in your calculator. Without using the pi, you could go 12 times 2 divided by 3 and then change that. Well, it looks like I don't have to change that into a fraction because I'm going to have this as cosine 8 pi plus, this will also be the same. Once you simplify one, the other one is the same. So making sure that your mode is in radians. So going to mode, going to radians. Now I'm going to actually solve for what this is equal to. And we would leave our answers just like that. So this is my answer. Now from this, we know what our radius would be and the angle. This is where we're going to keep it. Now, just kind of review when we have complex roots. Now, this is the power. We use this theorem. So when we find the power, what about when we find the roots of something? If we were to factor this, this would be x cubed plus 1 and x cubed minus 1 is equal to, this was supposed to be equal to 0. Sorry about that, is equal to 0. And then we'd have to keep on factoring that. Now you're going to have to just trust me, but because the fact that I could add this one and take the 6th root of that, that's going to give me a plus or minus 1. So I know that this could both be divisible by x plus 1 and x minus 1, And then we would have to use our quadratic formula to figure out if I were to use long division like we did in 4.2, but I'm not going to review all of that. We have x squared plus x plus 1 and x squared minus x plus 1. Both of these would be imaginary answers. So when I found the roots, if I use my quadratic formula, these two I could just solve, and I use my quadratic formula for these, I would get also x is equal to negative 1 plus or minus the square root of 3i divided by 2, and we'd also get x is equal to positive 1 plus or minus the square root of 3i divided by 2. So those would be all of our roots. Now when we have our roots, remember this is telling us we have 6 different roots. So these numbers should all be less than whatever our number we're starting here, same or less than. So now we also have a formula for that. So this formula, when we're finding the roots, what k is standing for is the root number. So n is the actual root, the number of roots. So this n is the same name as n here. So if I'm finding the third root, this n would be 3. If I'm finding the fourth root, this n would be 4. We have this k value though. The k value tells how many roots there are. Remember, if it's the 6th power, we should have 6 roots. We start here with z to the 0. So we start 0 to the 0, so that would be a 0 right here. Sorry. We start with 0 to the 0, that would be a 0 right here. That means we're not adding 2 pi at all. We have to figure out how many times around the circle. So typically when we're finding a root, if I'm finding the third root, it would look something like this. If I were to actually plot them, we would have a root someplace over here, we would have a root someplace over here, and we would have a root someplace over here, because there would be 3 different answers for a cubic root. So if I'm finding all 6 roots of 1 using this formula, so if I just write my z to the k first, when I'm reading this, this would be the 6th root of 1. So once we get into actual imaginary numbers, it's going to be a little bit different. But in this case, because that's 1, that's where this 1 is coming from. And then we're going to have in parentheses our cosine of our angle. In this case, the angle would be 0. And then again, if we did our tangent theta, we'll be doing that for the next one. And then we would have our plus 2 pi k divided by 6. Again, the 6 comes because of the n. And then we have a plus. I should have used, I'm going to write it up here, I sine of 0 plus 2 pi k divided by 6. Now, one thing once you're doing this, you're going to notice that it's going to be reoccurring a lot. So if I have z to the 0, this is my first root I'm finding. Right here, this stays as my 6th root of 1 is still going to be 1. Because this is 0, this is where I'm going to plug 0 in for k. So I'm going to have 0 divided by 6. So this will be cosine of 0. And I'm going to have a plus I sine of 0. The nice thing again here is whatever angle you get for this is going to be the same angle for this one. So where is cosine 0? Where is sine 0? That would be the same thing as 1 cosine 0 is 1 plus 0i. So this would just be equal to 1. So now if I look at my next root, so my second root that I have here, now I have as a 1. So when I plug this in, this is still 1. Now this would be cosine. I plug 1 into this spot right here. So this becomes 2 pi, because 2 pi times 1 would be 2 pi divided by 2 is 3 pi plus I sine of 3 pi. And if I evaluate that now, cosine of 3 pi, pi over 3, because it would be 2 pi divided by 6, which is pi over 3, and pi over 3. So cosine of pi over 3, that's my adjacent. My adjacent is going to be 1/2, plus my imaginary would be my opposite, square root 3i over 2. So here are 2 of my 6 roots. And I do the same thing for z2, z3, z4, z5. Because we start at z0, we only go to 1 less. So that's where this negative 1 comes from, 1 less. So filling in, when I plug in 2 for k right here, I would get 2 pi over 3. If I plug 3 in for k, I would get pi. If I plug 4 in for k, I would get 4 pi over 3. And the last but not least, if I plug 5 in for k, I would get 5 pi over 3, because you're simplifying that fraction. So all of these have a reference angle besides cosine of 60 degrees. Now if I look at each one of these individually, Depending on what quadrant it is, this is negative 1/2 plus square root of 3 over 2i. My next root, because it's just pi, would just be negative 1. Looking at your unit circle, that might help you. Again, this one, negative 1/2 minus square root of 3 over 2i because of what quadrant it's in. And the last one, at least 1/2 minus square root of 3 over 2i. So when I'm working with those, I typically will not do a sixth root, but this would be my 6 different answers. Now let's go into cubic. So if I found 3 cubes of this right here, first I have to figure out my r and I have to figure out my angle. So my r value, r is going to be the square root of negative 2 squared plus 2 squared, which would be 4 plus 4, which would be the square root of 8. So that would be 4 square root 2. That's my first answer. However, we can also leave it at square root 8, and I'll show you that in a second. And we have our angle. Tan of our angle is equal to our b over a. So in this case, my angle, because I'm going negative 2, positive is right here. This is the same thing as negative 1 and 1, so that would be a reference angle of pi over 4. So this angle right here, the second quadrant, this is pi over 4, 2 pi over 4, 3 pi over 4. My angle here is 3 pi over 4. Now if I write my equation z to the sub k, so that's where I'm looking at, z to the sub k, because we're going to have 3 different answers here. First, if we focus in right here, I can simplify that. I will be simplifying that for the rest of my 3 roots. But when we have a cubic root, that's the same thing as 1/3 power, and we have a square root, that's the same thing as a 1/2 power. So really what we have going here is 8 to the 1/6 power, because we multiply those together. So when I do this z to the 0 power, my first root, this number, my r, is actually my 6th root of 8. This simplifies to my 6th root of 8. So I have this 0 here. That means I'm not adding 2 pi on at all, because 2 pi times 0 will give me 0. Now sometimes people have troubles with this. If you have troubles with this, what you can do is just do 3 divided by 4, divide by 3, and then change that to a fraction. So I have 1 pi. So notice I'm not including the pi into that problem. So I have 1 pi. This is cosine of pi over 4. And get this, and this one should always simplify to be the same number. So now, when I'm looking at this, I have the 6th root of 8. You could have also actually simplified this, because the 8 to the 1/3 power is 2. So this is also the same thing as the square root of 2. And then the cosine of pi over 4 is going to give me 1 over square root 2. And then plus, I forgot my I right here. The square sine of pi over 4 is 1 over square root 2. So when I simplify this, I can multiply this in, and this actually becomes 1 plus I. 1 plus I. The next numbers are not going to be so nice. I'm going to pause the video and write out z sub 1 and sub 2 first. So you might want to do that first. So I pause the video and check over when you wrote out your z sub 1, z sub 2. One thing again, when I'm looking at those fractions, the example for this, I did 3/4 plus 4, because when I plug 2 into this equation, that would get 2 times 2, that's where that 4 comes from. And then I pushed enter, divide it by 3, and change that to a fraction. That's where that 19/12 pi, because I did not multiply by pi at all. Sorry about that, Claire. Now when I'm doing this, because right here, this is in pi units, and I've been using pi units, I can type this now into my calculator, making sure that my mode is in radians, which it is. Because of my pi units, I'm in radians. So if I simplify this, I can have second square root 2, and then make sure your arrow over, cosine 19 pi divide by 12, close your parenthesis. So this first unit, and I'm working on this z sub 2, would be 0.3660. That's my real part. Now I do the same thing. So what I'm going to do, I'm kind of going to cheat a little. Same thing, except now it's with sine. So now this is going to be minus 1.3660i. That's my second root. I want you to pause the video and try to do this root, z sub 1 root, right now by yourself. And you should have gotten, here's my real part, here's my imaginary part. You might be like, wait, is this always going to happen? Well, not always. However, because the fact that we have this 3 zeros and we're looking at a quadrants because of our zeros, in this case, it works because it's cubic. It's not always going to be the case. There you have it. You have one root here and you have two roots here. So those are the 3 cubic roots of my imaginary number, -2 plus 2i. And that's all we have for you today. Have a wonderful day.